Hi everyone, my name is Sberlo, and I will talk about error reduction for weighted PRGs against read-once branching programs. This is joint work with Gil Cohen, Dean Doron, Oren Renard, and Amnon Tashma. So let's briefly go over the basic setting. So L is the class of problems that can be solved deterministically by a log space algorithm. BPL is the problems that can be solved by a randomized algorithm with two-sided error that uses log space, and RL similarly, but with one-sided error. And the big question, the BPL versus L question. So the approach in analyzing log space computation is reducing to a slightly more convenient computational model called read-once branching programs, and I'll abbreviate and just say BP instead throughout the talk. So an NW sigma BP is simply a layered graph of n+1 layers. Each consists of W vertices. So this looks like this. You can see here 6 layers, so n equals 5, and is also called the length of the BP. W equals 4. W is called the width of the BP. You can see that every vertex have outgoing edges labeled by a distinct symbol from sigma. Here, sigma is the binary alphabet. And also there is a start vertex at the first layer, and each vertex on the last layer is either labeled with accept or reject. And how computation looks like or defined in this model. So you have an input, it is n symbols from sigma. You start from the start vertex and you go according to the labels. And if you reach an accepting vertex, you accept. And if you reach a rejecting vertex, you reject. That's it. And a convenient notation is this. For input x, we write b of x equals 1 if the BP accepts the input and 0 otherwise. And this is convenient because now the expected value of this b of x is exactly equals the probability that a uniformly chosen random input will be accepted by the BP. Good. So what BPs have to do with randomized log space computation? So this is the correspondence. A randomized algorithm with a fixed input corresponds to a BP as follows. So the input to the BP is actually the random coin tosses for the algorithm. And so, the length corresponds to the number of coin tosses. And usually this can be thought as the running time of the algorithm. The space corresponds to the width to W, and more accurately, the space roughly equals log W. And this means that if your algorithm has a two-sided error at most 1/3, then the acceptance probability of the BP over a random input is at least 2/3, and otherwise at most 1/3. Good. So one approach to de-randomization is using pseudo-random generators, which are basically a way of taking few truly random bits and extending those to n pseudo-random bits, and use the pseudo-random bits in your algorithm and hope that it works roughly the same. So a definition in our setting, an NW sigma epsilon PRG with seed length S is simply a function that takes S bits to N bits, such that, and this is the important requirement, for any NW sigma BP, we have that if you take a truly random seed to your generator and then feed that to the BP, then the acceptance probability approximates the true acceptance probability when the BP reads a truly random input, up to an additive term of epsilon. So the existence of explicit PRGs implies de-randomization, specifically if you have a length n with poly n and small constant error PRG with logarithmic seed length, then BPL equals L. And by explicit, I mean that you can compute this function in low space. And non-explicitly, we do know that such functions exist with amazing seed length, which is basically logarithmic in every parameter. So one way to de-randomize, one prominent way of de-randomizing algorithms is approximating this acceptance probability. And you can do that via an algorithm, and I'll mention one in the next slide. But PRGs offer a very unique form of approximation to this acceptance probability, which is the average acceptance probability over small sets of inputs, obviously given n, w, and epsilon. So this is the approximation for the acceptance probability that a PRG will give you. And when you look at it, you say, well, why just consider a simple average? Why not consider a weighted average? And this is exactly what Braverman, Cohen, and Garg did. This turned out to be useful for them, very useful. So formally, a PRG outputs, given a seed, it outputs a sequence of symbols, but now a weighted PRG will also assign a weight for every sequence of symbols that it outputs. And this weight can be arbitrary, it can be negative, it can be very large, it can be very small, it can be anything. So the only requirement is that still this weighted average, when you take your weights, approximates the true acceptance probability. So this is the definition of weighted PRGs. And obviously you want explicit ones. And for all intents and purposes, weighted PRGs can replace PRGs. For instance, they will give you a hidden set generator and actually a bit more. Not only that, in a paper that I'm going to mention quite a few by Pine and Batten, so they showed that in a certain model of computation called permutation branch program, so it's sort of a restricted model with an asterisk, then this is actually strictly stronger than regular PRGs, this notion of weighted PRG. Okay, so enough with the digression. Let's start with what are the known results in this general setting of BPs and PRGs. So we have the Nissen generator and the Pagliazzo-Nissen Wiggerson generator that gives you seed log n times log n w over epsilon. Good. I said that I will mention an algorithm. This is sort of the state, almost the state of the art up to log factors that I'll mention in the end. An algorithm by Sachs and Zhou for approximating the acceptance probability, hence the randomizing log space algorithm, by an algorithm that uses a deterministic algorithm that uses log to the power of 3/2. And I want to stress this is an algorithm, not a PRG. Okay, we also, due to a recent line of work initiated by Braverman, Cohen, and Garg, they gave a weighted PRG with improved dependence on the epsilon. So you can see that this is the seed length that they gave. This O tilde means that they are hiding log factors, but you can see that this is similar to the INW, but now the log 1 over epsilon is not multiplied by log n. It's in the INW or Nissen generator. So we have improved dependence in this error term. So the same year, after the BCG paper, Hase-Zuckerman gave a hidden set generator for the case where W is a poly n. So it is log squared n plus log 1 over epsilon, actually without the log factors. And Chedapurier and Leo gave a weighted PRG, also weighted PRG, sort of similar, but slightly different, slightly perhaps less involved than the BCG, with roughly this seed length, perhaps with a different, better dependence in the log factors. So this is about weighted PRGs and this line of work that improves the dependence on the error parameter. And there is also one work by Raz and Rangel. They gave sort of a white box PRG. I don't want to formally define what it means. And they also assume that you know the probability that a random input reaches every state. So they gave, in this sort of setting, this seed length. So you can see here the improved dependence on the width parameter. This log W is not multiplied by log n as in the Nissen and the INW generators, or even these generators. So I don't want to get into the Raz-Rangel too much. I'll just say sort of the essence of what I mean by knowing the state probabilities why this is sort of still interesting. So note that even if you know the true acceptance probability, you know that it is 0.94, then it is still not trivial to give like actual inputs, that small set of inputs, that the acceptance probability, the average acceptance probability of those inputs actually really approximates the true acceptance probability, even if you know the answer. So that's what I had to say about the Res-Wrangle result. So in light of this, Braverman, Cohen, and Garg made a very interesting observation, is that if you have an explicit weighted PRG, even weighted PRG, with simultaneously improved dependence on the width and the error parameter, specifically if you get log squared n plus log w plus log 1 over epsilon, then this immediately improves the de-randomization for BPL using the Sachs and Jones framework. And this was actually formalized later in the Chattapudi and Liao. And this serves as a great motivation for studying these problems if you're interested in the BPL versus L question. Good. So we're in a position to state our results. Let me just say that the paper that I've already mentioned by Pine and Vadan, which is actually in this conference as well, achieved this exact result independently. Perhaps not in this formulation, perhaps with slightly different parameters, very slightly, but the main idea is really the same. So what is our result? Let me tell you, this is basically an error reduction. So you start with any PRG that you want, and n sigma w epsilon 0 PRG with seed length as 0, then we construct another PRG still for with w BP of the same length and over the same alphabet, but with a smaller error, error epsilon rather than epsilon 0. Epsilon is smaller than epsilon 0, and essentially there is no real overhead in the seed of the generator that we construct. You can see this is the original seed plus this. So if you ignore this log term, then you can see that you simply add log w plus log 1 over epsilon, which is unavoidable if you want to have a PRG against with w BPs and their epsilon. And also there is no real overhead in the space complexity of the PRG, and naturally the space complexity of PRG is also important, whether if you want to use the PRG directly or through an elaborate de-randomization scheme such as Sachs and Jones. Okay, so there are two obvious caveats. First, that it is a weighted PRG, not a regular PRG. This is one caveat. We would like to have a regular PRG. And the second one is that the error that you start with has to be smaller than 1 over the length, 1 over n. And this reflects on the seed length of the initial PRG that you start with. But again, the main contribution is that this is an error reduction. This works regardless of the PRG that you start with. You can start with any PRG that you like. And so, for instance, if you improve the dependence on the width parameter, and you use the observation in the previous slide, then congratulations, you have improved the de-randomization for BPL using this error reduction. And if you use this error reduction with known PRGs such as the INW or the Nissen generator, we actually handpick which one to use, but you basically reproduce the parameters of the Braverman, Cohen, and Garg, the Chattapudi and Liao, the Hose-Zuckerman heating set generator. Yeah, so this is the main result, this error reduction. Good. So let me start with the analysis. So the analysis, the construction, the proof. So the story begins at something called the Richardson iterations, which is basically a procedure that takes a moderate approximation and make it better. And let me be slightly more concrete. So suppose you have a matrix L and you want to approximate its inverse, and you have a moderate approximation for its inverse, which we denote by A, then this expression right here is the better approximation for the inverse of L, where if you take K to be, the larger you take K, the better this approximation becomes. So this is a bit of a digression what this has to do with BPs, but I'll explain this in the next slide. And this is formally what it means. You choose the notion of approximation to be a submultiplicative norm, any submultiplicative norm that you like. And you can see that if you start with an epsilon approximation, you get epsilon to the K. You also pay the norm of this matrix L and its inverse. And this is actually important, but for the simplicity of the presentation, just forget about it. You reduce the error from epsilon to the K. And the usage of our usage of the Richardson iterations is inspired by a really nice work by Ahmadinejad, Kellner, Mota, Peebles, Sidford, and Badham. They adopted ideas from area called or the problem of Laplacian solvers in nearly linear time, and they use this Richardson iterations in this context. And this problem is very, 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 very much related to the problem of the BPL versus L question. I don't want to get into this, but this is definitely much inspired by what they did, and also what is in this slide. So this slide tries to explain what it has to do with BPs and PRGs. So suppose you have a BP, and we now make a little shift in terminology or notation or perspective. We're looking at something called the transition matrices. So this is simply the transition matrices of the graph that you look at in the BP. And formally, the transition matrices are simply the transition matrix AK is simply the probability that you move from I to J in layer K upon reading a random input. And basically, the product of the products of this transition matrices tells you what is the probability of moving here from the first layer to the last layer. In general, from the layer that you start with to the end layer. And if you know the probability of moving from one vertex to another, then you can definitely read off what is the probability of accepting. But this sort of ignores like what are the accept vertices. There are no accept vertices. You just, it's more general. Just ask what is the probability of moving from one vertex to another. So the point is now, instead of trying to approximate the acceptance probability, trying to approximate the matrix of the transition probabilities. So this is the shift. This is quite common, and to some extent, these are two equivalent. The quantitative consequences of this shift are actually significant, but for simplicity, again, these are sort of equivalent. All right. So main point, you have a BP. This is its transition matrices, and you are interested in computing this product of A1 to AN. Now, there is sort of a standard reduction from products, matrix products, and inverses, and this is such a reduction. So you consider this matrix, this block matrix, with the identity matrix on the main diagonal. You write the minus AIs beneath it, and then the inverse of this matrix is just this one. You can easily verify this, and you can see that the product of the AI is written in the leftmost bottom entry. So this is sort of the reduction. So now you have an inverse, which you want to approximate, and if you can moderately approximate it, then congratulations, you can use the Richardson iterations and get a better approximation, hence getting a better approximation for this product, which I said it is roughly as understanding the acceptance probability of the BP. Good. So the last missing piece of the puzzle is giving a moderate approximation for this inverse. So I wrote the inverse here succinctly. So what do? You simply use a PRG. So I wrote here like PRGs like sub I, which means that you output I symbols. You use PRGs that output I symbols. But again, for simplicity, think of just a sort of general purpose PRG that you ask, give me absolute random symbols from sigma, and this is the GI. So I'll sometimes just write G and ignore this subscript. Then you can use those PRGs to approximate this product. And again, this comes from this. So I define PRGs as approximating the acceptance probability, but again, in this terminology, so the acceptance probability of this product is basically, excuse me, and this product roughly to some extent is like understanding the acceptance probability of this sub BP from layer J to layer I. So this is this notation, BJI denotes the sub BP from layer J to layer I, and you can no longer talk in terms of accept, reject. So B of X is simply the sort of the transition matrix from the first to the last layer instead of just accept, reject. So this is actually a permutation, not a real probability for an input. So let's cut the story short. You just use a PRG to approximate these products, and this is quite standard. And sometimes even PRGs are constructed this way that they approximate this product. Good. So you use a PRG to approximate the inverse or get a moderate approximation for the inverse of L. And now you simply use the Richardson iterations and see what that gives you. So let's try to look at a very degenerate example in which we take one iteration for length 2 BP. Again, this is really degenerate. So your BP has two halves. Like this is the first half, this is the second half, this is the entire BP, the two-step BP. And the one iteration of the Richardson iterations looks like this. You take your moderate approximation, and there is one correction term. And the moderate approximation is simply the one that you can see that the PRG gives you. So for any product, this is the transition matrix of the first half approximated by the PRG. This is for the second half, and this is for the two halves together. So this is our moderate approximation to the inverse of L. And now if you, well, compute things, there is a direct computation here, but let me just focus on what comes out in the leftmost bottom block of this matrix, which is the what interests us. Yeah, this is what is supposed to approximate the true transition probability. So this looks like this. You can see here that you have in the first summon, you can see this A1, which is basically the true transition probability from the first layer to the second layer. So you can think of it as A1 just takes a random symbol from sigma, and then you continue the second half using the generator. So this first summon looks like using a random single symbol from sigma and just continue the second half with the generator. And the second summon looks like this, but in reverse. You start the first half with a generated sequence and then throw in a random symbol from sigma. And here you can see the third summon with a minus sign. So this gives you hints of where the weights come from, or well, where will the negative weights will come from. So you can see here that you take the first half with the generator and then independently the second half also with the generator. So this what happens in this sort of degenerate case, but it hints on what happens in the general case. So the general case sort of looks like this. So if you compute the general Richardson iterations, the point is, and this is like the first main observation, it looks like a weighted PRG. It looks like sums over weighted sum over sequences, true sequences for the BP. And how these sequences look like. So this average go iterates over all possible partitions to k+1 blocks. So in the previous example, k was 1 and we had 2 halves. Here we have k+1 chunks, and we basically partitioned the n length BP to k+1 chunks. And in each chunk, you basically use the generator independently, and you can see here the TIs, which are just bits, and the sigma i's which stands for throwing in a random sigma once in a while. So this is how those sequences looks like, and you basically have to iterate over all partitions, over all these possibilities of throwing sigmas once in a while. This is this definition of GBM. These are the sequences. And the weights, well, they are signed. You saw that in the previous generated example, we had two segments with a plus sign and one with a minus sign. This depends on how many times you throw in a sigma. And this terms come simply from normalization, because if you insist of presenting this matrix as an expectation, as sort of a convex sum, then you need those weights to be large. You need to sort of normalize. So you can see that this is a weighted PRG. Very nice. The problem with this is that this is way too costly. And the reason this is too expensive is because you cannot really afford to run your PRG independently k times with k-independent seeds. So the solution is quite straightforward. Is don't do that. Instead of using independent seed, just use an auxiliary PRG to produce pseudo-random seeds for those chunks, and use those pseudo-random seeds instead. And this works, and it looks like this. This is how the general construction looks like. These G is the PRG that you start with. You can see here that it uses seeds, but these seeds are not like independently drawn. They are drawn from an auxiliary PRG. And the overall seed for the generator is the seed for the auxiliary PRG, plus the seed that determines the partitions and when to throw in the random sigmas once in a while. So this is it. This is the entire error reduction. Well, the analysis is quite easy, because you know the Richardson iterations work if you take independent seeds for the chunks. So this gives you an epsilon to the k approximation, and you just need to argue that by using pseudo-random seed, you haven't done much damage. And this is true, and this is actually a simple union. So this completes the construction and the analysis, and I'm basically done. But I really want to mention a very nice follow-up work by Hoza. So Hoza constructed using these ideas of the Richardson iterations, this error reduction, and some other ideas, and length n with poly n actually, and error epsilon, weighted PRG with seed length without the log-log factors, which is actually exactly as the Hoza-Zuckerman hitting set generator, but this is a weighted PRG. And he actually needed it to be a weighted PRG and not a heating set generator, because he used this in the Saxton-Joe frameworks to shave this square root of log-log factor. Very nice. So let me finish with few open problems. One open problem is removing the requirement that the initial error is smaller than 1/n. And this was actually, we don't know how to do this in the general case, but in the paper that I've kept mentioning by Pine and Vadam, they actually circumvented this requirement in the restricted model of permutation branching programs. So this is very interesting. If you enjoyed this talk and you enjoyed this video, and even if you didn't, you definitely should check out their video. So another problem is obtaining a regular PRG rather than a weighted PRG, or perhaps get a better understanding on the weight behavior, or with a different construction, with this construction. Another problem is obviously improving the dependence on the width parameter, and you can ask all of the above questions in reasonable, respectable, restricted models of branching programs. Good. So thank you very much for your attention.